Lecture 39, Multiple Integral. Now discuss the geometrical interpretation of integral. So if we say fx is a function in the interval x equal to ab, and then integration a to b fx dx is what is numerically equal to the region bounded by the curve, that is the curve fx, and x-axis, that's an x-axis, and the straight line x equal to a and x equal to b. So these are two lines, x equal to a and x equal to b. So we write what the integration a to b fx dx is what is an area of that bounded region a b c d. So integration is what is just, and through the integration we can just find the area bounded by that curve below that curve and above that x-axis, or we can say an algebraic sum of the area of that particular shaded region bounded by that curve and the lines x equal to a and x equal to b. Now the double integration. So when we integrate a function of two variables, it means we will integrate over the region r square, that is two-dimensional space. Now assuming that the region is R2, that is two dimension, is a rectangle. If it is rectangle, then which we will denote as, suppose we take a region x1 x2 and y1 y2, this means that the range of x and y, we get x1 to x2 and y1 to y2. So here we discuss the two cases because you have to understand the concept of area and volume through the double integral. So suppose if we want to find the area of the region bounded by the two curves as shown in below. In that graph, if you see, we have two graphs, y1 is equal to gx and y2 is equal to, that is, fx. So the bounded region between these curves, we have to find the bounded region, that is, says capital D. So we use the area of bounded region, we use the double integration, we integrate a to b and integration gx to fx dx dy. Here the limit of y is what, gx to fx, and when we integrate, first we integrate with respect to dy, then the constant limit x equal to a is equal to x equal to b. So through this we can find the region between these two curve, bounded region between these two curve. Here you have to notice that the area, this area or the region can be found by the single integration. How? If you take a to b and take the difference fx minus gx dx, so we get a region or the area of that region, that is d. And another way, and if you want to evaluate the volume, so if suppose we take a function fx is greater than equal to 0, so start with the graph, that graph surface, because fxy, what is fxy, this is the function fxy, this is the surface. So the given graph is fxy over the rectangle, that is a rectangle r. So the volume, if we integrate that surface on that region, when where x is taken a to b and y is taken c to d, so this is the region where we evaluate the surface. So if we integrate that surface on that region, so the limit a to b, that is the limit of x, and c to d, that is the limit of dy, and we are taking a function means that's a surface, so we obtain the volume. So you have to, here you have to notice that if you are doing double integral between the two curves, you get a region or a area, and when you are integrating the surface, that is fxy, the surface in the particular region, so you get a volume. So that's the basic difference. Here we take fxy, we are integrating a surface between the limits, and here we are just integrating between the double integration between the two curves. Now discuss the evaluation of double integral. So if there are two type of region that we have to look at here, let the region R be bounded by the curve says x equal to x1, x equal to x2, and y equal to y1 and y equal to y2. These x1, x2 and y1, y2 may be a function. So here we take a first case when x1 and x2 are a function of y, that is we can say x is equal to phi 1 y and x is equal to phi 2 y, means we are taking these are two curve, and the y1 y2, the limit y1 y2 is constant. It means we take the integration with respect to x then y. So here uh, the limit, or we can say the limit of y is what is constant, that is y, and say this is x, and these are two curves, means the x1 is in the form of y and x2 is in the form of y. These are two curves. So if we are taking the limit the limit of x in terms of y, and y, the limit of y is taken as a constant, so if this is y1 and say this is y2, so in that case the integration double integral we are evaluating, first we are evaluating with respect to x, we are taking the integration first way with respect to x and substitute the limit, then the remaining function we are obtain with respect to integrate with respect to y. So what will happen here when we taking the integration with the first integration with respect to x, so what will happen that we are taking a small strip and which is expanding along the x-axis, then we are taking the integration within the constant limits, then the strip is expanding in that direction, so we obtain the complete region which is bounded by that lines and these curves. So here you have to notice that what we are taking a strip is that is PQ, and we are taking a small region del y. So here the double integral is evaluated first with respect to x, treating y as a constant, means when you are taking the integration with respect to x, treating y as a constant, and the resulting expression which is a function of y is integrating with respect to y between the constant limit y equal to y1 and y2. So in that way we are evaluating the double integral if we are taking x1 and x2 is a function of y and the limit of y1 y2, that is the limit of y in constant term. So case 2 is just reverse of the case 1. If we are taking y1 y2 are a function of x, that is y is equal to phi 1 and y2 equal to phi 2x, and x1 x2 are a constant. So you can see that graph, these are we have two functions y2 and y1, and these are two lines, that is x is equal to, we say this is x1 and says this is x2. So between that region we have to find the region. So the double, by the using a double integration, if we are taking the limit of y in the terms of x, so first we integrate with respect to y, and the resulting we integrate with respect to x. So in that case the physical interpretation is same as in the previous case. When we are integrating with respect to y, so it means a small region del x is expanding along the y-axis, and when we are taking the resultant, we are taking integration with respect to x, so it will be expanding along the y-axis. So in that way we obtain the complete region. One more case we are discussing here, that is case 3. If suppose x1 x2 the limit of x is constant, and the limit of y is also constant. Y1 is c and y2 is d. Means we are integrating between the rectangle. So in that case, when we are evaluating a double integral, the order of integration has no mean. Means either you are taking first you are taking the integration with respect to x, or either you are taking with respect to y. So the order of integration has no sense. So we start with a simple example. Here we have to evaluate that integral 1 to 2, 4 to 3 xy plus e raised to power y dy dx. So here first you have to identify which is the limit of y and x. So as you see, the order of integration dy dx. So we can say the limit of y is what? 3 to 4, that is a yellow color, and the limit of x is what? 1 to 2. So here the both the limit are what? Constant. So you can take the integration first with respect to x or with respect to y. So the order of integration doesn't matter in that case, because the both the limit are constant. So we start the order of integration. So first we take the integration with respect to y. So 1 to 2. Now take the integration. When you're taking the integration of that function with respect to y, so treating x as a constant, what we get? So we get x y square by 2 plus the e raised to power y. We write e raised to power y. Now apply the limit 3 to 4 dx. So here when you apply the limit integration 1 to 2, so we get the upper limit, we get 16 x by 2 plus e raised to power 4, to the lower limit 9x by 2 minus e raised to power 3. Now that is the resulting integration. You integrate that with respect to x. Now when we take the integration with respect to x, so we get 16x square by 4 e raised to power 4, that is a constant term, 9x square by 4, and that is x e raised to power 3. Now apply the limit 1 to 2. Now applying the limit, we get 16 into 2, 4 by 4 plus 4 e raised to power 4, 9, 4, uh, 4, sorry, 2 e raised to power 3. Now apply the lower limit, we get 16 by 4 minus e raised to power 4 plus 9 by 4 and plus e raised to power 3. When you simplify this, what will we get? 21 by 4 and this plus e raised to power 4 minus e raised to power 3. So this is the resultant on evaluation that integral. So in that way we can easily evaluate the integration. Now one more example here. Again we have an double integration and we have to evaluate here, and the limit of integrations are constant. So you can take the integration first with respect to x or with respect to y. So if we taking the integration first with respect to, we can say with respect to x, so you write 1 minus x square 1 minus y square. So when you're taking the integration with respect to x, so treating y as a constant, so what we get 0 to 1, so the integration of 1 upon 1 root 1 minus x square, we get sine inverse x, and that function is taking constant. I apply the limit 0 to 1 dy 0 to 1. After applying the limit sine inverse 1, we get pi by 2, and sine inverse 0 gets 0, and the function root 1 minus y squared dy. Now take the integration with respect to y. So the pi by 2 is constant term. The integration of 1 upon root 1 minus y square, we get sine inverse y by the limit. So we get pi by 2, again the pi by 2 minus 0. So we get the result pi square by 4. So on evaluating that integration, we get pi square by 4. So in the constant limit, you can integrate first with respect to x, then with respect to y, or first you can take integration with respect to y, or then with respect to x, you get the same result. So you take an example, evaluate the integration 0 to 1 and 0 to root 1 plus x square d by dx. The function is 1 plus x square plus y square. So here you have to notice that the limit, the one limit is what is not constant, which is 1 plus under root 1 plus x square. So here you have to identify the limit of integration. So that limit is what? It is in the term of x. So we can say this is the limit of y and this is the limit of x. So here the limit of y is not constant, it's in a term of function. So we take the integration first with respect to y. Now we take the integration 0 to 1, 0 to 1 plus x square root 1 plus x square plus y square dy. Then we take the integration with respect to x. Now here the function is what? We are taking the integration with respect to y, so treating x as a constant. So you are remember the integration of 1 upon a square plus x square, that is 0 to 1 upon a. So here we write 1 plus x square tan inverse y upon root 1 plus x square. Now apply the limit. Limit is 0 to 1 plus root 1 plus x square. The resulting, we take the integration with respect to x. Now apply the limit. We get 0 to 1 upon root 1 plus x square. When you apply the upper limit, tan inverse 1, and tan inverse 1 is what? Is pi by 4. Now when you apply the lower limit, so we get tan inverse 0, we get 0, and this resultant, you take the integration with respect to x. So here pi by 4 is constant, and the integration of 1 upon 1 plus root x square is what? Is log x plus root 1 plus x square. Apply the limit 0 to 1. So when you apply the limit, you get pi by 4, the upper limit log 1, and this is we get 1. So we get log 1 plus root 2, and we have to use the lower limit. So we get log 1, and log 1 is what? 0. We can say we obtain the result pi by 4 log 1 plus root 2. So in that way you can easily evaluate the double integration. Here you have to remember the limit or order of integration. Thank you. Continue the next lecture.